All right, let's talk about activity 17, which is about fixing errors. We're going to start here. This is the assignment paper. Let's start by reviewing ASCII. Here's a table that has the character, the ASCII value of that character. All right, so space is 0, 1, 0, 0, 0, 0, 0, and so on and so forth. And this is the binary value. So if the filled circle means count me, what is decimal value of the following? So that's easy. We look at, we know here's 1, plus 4 is 5, plus 8 is 13, plus 64. So it's 64 plus 13, and so the decimal value is 77. And actually a sanity check on that is look at this, we know it's going to be odd. What is the corresponding binary value in ones and zeros? All right, so that's easy. Wherever there's a filled in circle, that's going to be a 1. Wherever it's not filled in, it's a 0. So it's 1, 0, 0, 1, 1, 0, 1. Using the following ASCII table, what are the 7-bit ASCII values for the character CDM? So that's easy. We will look for C, it's all uppercase. And so that's C. And then we want D. And M. Okay, so that's the ASCII value of CDM. What if we wanted to send a message cool to a friend in response to something they sent to you? Your cell phone would convert each character ASCII, giving the following. So this would correspond to C-O-O-L. Notice these are both the same. Unfortunately, there's always some noise on the transmission line, so sometimes they get sent incorrectly, right? So what would happen if noise messed up the first letter of your message? So it should be ending with a 1. So what's actually entered here, or what actually is sent, is 110010. So that would be 110010. Let's look for it. 11000. Let's see. 00010. So a lowercase b. So it would say bull. So this would say this. This would be, instead of what you think it is b. And actually be lowercase b, and then it'd be uppercase O-O-L, like that. Okay, so that's the message that's actually delivered. So what we're going to talk about is ways there are of catching that an error was actually sent, because how would we know? All right, so there are a number of techniques we use, and one way is called parity check. So parity check, they just add another bit to the end, and the bit's a 0 or 1. And if the number of ones is an even number, then they put a 0. If the number of ones in the number is odd, then they put a 1. And that way they know, then they look and see how many ones there are in there, and if it's an even number or odd number. Okay, so in this case, we have 1, 2, 3, 4 ones, and the sum is an even number of ones. Therefore, parity bit of 0 is added. So the parity bit here would be 0. Whoop. In this case. And in this case, it would be a 1 because it's an odd number of ones. So let's assume transmitter wants to send the letter C, thus it would be 11000011. The parity bit of 0 is added to the end because it's an even number of ones, and when it's sent, this number turns from a 1 to a 0. So the receiver says, here comes a 0 at the parity bit, therefore it must be an even, an odd number of ones. So we get 1, 2, 3. Okay, so 0 says that there's an even number of ones, and there isn't. There's an odd number of ones. There's 3. Therefore, there's an error. And that's because the 0 at the end of this thing right here, the 0 says there should be an odd number of ones in this transmission, but there aren't. There is, and there should be an even number of ones, and there aren't. There's an odd number. Okay, so therefore there's an error. Is there a parity error? If the character 11000100 is received, is there a parity error? Okay, so the answer is no, because there's a parity bit. If the parity bit equals 1, then we have an even number of ones. If the period bit equals 0, then we have an odd number of ones. And there is an odd number of ones. Okay. So period check's not the only way to identify errors, and the errors don't always involve computers. Okay, so Swiss and German railways use a special system to reduce errors when the locomotive numbers are recorded. So there's a 7-digit train number. And the first 6 digits are the actual train number, while the 7th is a check digit. All right, so to demonstrate how this works, you do the following. Add the first, third, fifth, and 7th digit. For example, the train number is 162-943-7, and you add the first, the third, the fifth, and the 7th. You add them together, and that gives you 14. Then you have the second, the fourth, and the 6th, and you double that. It's quite complicated. That gives you 18, then double gives you 36. So you add them up and double them. Now you add them two together, and if the final sum is a multiple of 10, then it's probably okay. If not a multiple of 10. Okay, so let's see. 153, 5246. So we're going to add the first, the third, the fifth, and the 7th. The first is 1, the third is 3, the fifth is 2, and the 7th is 6. All right, that equals 9, 10, 11, that equals 12. Okay, now we're going to add the second, the fourth, and the 6th. So we had 5. The fourth is 5, and the 6th is 4, and that equals 14. And we're going to double that, and that equals 28. So 28 plus 12 equals 40. Is it a multiple of 10? Yes. Multiple of 10. Okay, now let's look at this one. Probably wrong, so we have an example that's wrong, but let's see. Okay, 1 plus third digit is 4 plus the fifth digit equals, and plus the 7th digit. And that equals 7, that equals 10. And we want the second digit, which is 3, plus the fourth digit, which is 8, plus the sixth digit, which is 4. And that equals 11 plus 15 times 2 equals 30. This is yes. Okay, so 30, it equals 40, right? 30 plus 10 equals 40. So yes, multiple of 10. Okay, this is called an arithmetic checksum. It's used a lot on the internet kind of stuff. So let's go back to parity errors. This can be, let's see what we got here. So just a parity error without knowing what's originally sent. Does the receiver know which character it is? No, because it only tells us if there's an error or not. So when it does receive a parity check and it checks the number of ones and knows that it's odd, then it knows it's wrong. So you can't really tell which of the bits has been flipped. All right. So let's say this is what we wanted to send. Okay. And this is what we send. And if you look at it, let's see where the bit got flipped. Actually, I don't see the bit. Oh, right here. Okay, so that's where the bit got flipped. All right. Okay, so the way this worked, this is a number that we're trying to send. This is this is the number we want to send. So what we do is we take each of these and we triple it. All right, so we send 3 ones, 3 zeros, 3 ones, and each of these corresponds to here, right? So let me see if I can throw an arrow in there or something. Shape, arrow. Okay, so this corresponds to that. All right, this corresponds to this. All right, and so on and so forth. Okay, now they should all be the same number, right? Because they're triple. This one shows it's different, so we know it's 0, 1, 2, 1, 2, 3, 4. It's the 5th bit that was altered. Okay, because we tripled each one before we sent it. And then the receiver knows that, oh, okay, this one isn't the same as these other 2 digits, therefore we need to change that to a 1. So it self-corrects. It's error correction. You can read this about the space shuttle. And let's see what else. Oh, there's another way of checking it. This is using a Venn diagram to explain it. But what they did basically is you have 4 bits. So in this case, we have 0, 1, 0, 1. We label each of these as D1, D2, D3, D4. And we set a parity bit for groups of them. So 0, let's see, D1, D2, and D4, they have 0, 1, 1, so they have an even number of ones, therefore we set the parity bit to 0. And then we have to set the D1, D2, and D4 are represented together. We set that parity bit to 1 because it's an odd number. And then P3, there's 2 1s, therefore we set the parity bit to 0. All right, and then it can figure out what's wrong based on this Venn diagram. You can read this, but you're not going to have to do it. Okay, so let's see what we got here. So we want to send the data 1, 1, 1, 0. And there are 3 parity bits that we have to generate. So what we have together is D1, D2, and D4. So D1, D2, and D4. And so the parity bit for that is there's an even number of ones. Therefore, make sure that I do this right. There's an even number of ones, therefore we set it to 0. So the parity bit for this is going to be 0. And then the second breakup is, let's see, D1, D2, and D4. So that's 1. Okay, so this doesn't look right. Let me see. I think he's made a mistake here in this layout. D1, D2, D4. See. Check, we'll check. D1, D2, D4, D1, D3, D4 is what this should be. So this is incorrect actually. This is D1, D3, D4. Okay. So we have D1, D3, and D4. Again, that's a 0. And then we have, let's see, D2, D3, D4. So D2, D3, and D4. And again, okay, so the parity bits are 0, 0, and 0. Okay, so in this case, 0, 1, 0, 1 was what we wanted to transmit, and 0, 1, 0, and then using this Venn diagram, you would figure out what will be wrong. Now we pretend, so here's what we got to do. So the parity bit value is going to be 0, 0, 0. Now pretend that the data has been sent to someone, and during the transmission, the first bit is changed to a 0. So it'll be 0, 1, 0, 1, 1, 0, 1, 1, 0, and we're going to send this parity check of 0, 0, 0. So right away we're going to know, when it looks at this, it's going to say this should be an even number of ones and it's not. So we know right where that's wrong. This parity bit is going to show that something's wrong. Okay, so that is it for activity 17. If you have any questions, please email, put in your answers and submit it to your Dropbox, and enjoy.